Welcome back to the deep dive. We are doing something a little unusual today. Typically, we take a specific event, a piece of tech or a historical figure, and we drill down until we hit bedrock. But today, we're zooming out, way out.
Yeah, we're looking at the bedrock itself.
We are looking at the bedrock. Literally.
Literally. We're talking about the hardware, the machine.
Yeah.
Planet Earth.
Exactly. And, I was looking through this stack of research we have. It's primarily centered around this massive visual guide called Earth Knowledge Genius. And my first thought was, okay, geology, rocks. I know this.
Right.
I live here. I walk on the crust every day. It feels familiar.
Well, we all treat it like a rental car, don't we?
Right.
We drive it hard. We might, complain about the weather a bit.
Right, the local conditions.
But we rarely pop the hood to see how the engine actually works.
That is the perfect analogy. It's absolutely perfect. And the more I read through this, the more I realized I have absolutely no idea how to operate this vehicle. So the mission for this deep dive is to basically draft a user's manual for Earth. We want to move beyond the basic geography we all learned in grade school and really uncover the mechanics. Because when you look at the specs of this planet, they are, frankly, terrifying.
Terrifying is a fair word. It really is. We tend to think of Earth as this stable, solid foundation. It's terra firma, right? That's the whole concept.
Solid as a rock.
But the data, it paints a picture of a violent, restless, screamingly hot rock hurtling through a vacuum. It is a system that is constantly erupting, flowing, and recycling itself.
It's a miracle we're here at all. It really is. And to give you, the listener, a taste of the I can't believe that's true nuggets we're going to uncover today, let's just tease a few.
Yeah.
For one, the days are getting longer.
They are. It's a slow grind, but the physics of it are they're undeniable.
We're also going to talk about a desert where it hasn't rained in 400 years, which, by the way, is probably not where you think it is.
Almost certainly not.
And purely because I am 12 years old at heart, we are going to discuss fossilized dinosaur poop that weighs as much as a medium-sized dog.
The scientific term is coprolite, but yes, it is a very heavy, very preserved piece of biological history, a very personal piece.
It is. So let's open the manual. Section 1, the cosmic context. We need to establish where this machine is parked.
Right. We're the third rock from the sun. And in the context of our solar system, Earth it's an anomaly. The guide we're looking at refers to it as the Goldilocks planet.
Okay, so because the porridge is just right. That whole story.
Exactly. But it's more than just a cute story. It's all about what scientists call the habitable zone. If we were just a little bit closer, like Venus, we'd be a runaway greenhouse pressure cooker. It's hundreds of degrees on the surface there.
Unlivable.
Completely. And if we were a little further out, say where Mars is, we'd be a frozen, radiated wasteland. We are in this tiny, fragile sliver of space. Just this little orbital ribbon where liquid water can exist on the surface.
And that water is the defining feature, isn't it? That's why we call it the blue planet.
It is. I mean, nearly 75% of the surface is covered in water.
Yeah.
That is totally unique in our neighborhood. But there's another stat in the data that really caught me off guard, and it speaks to that hardware aspect we mentioned earlier.
Oh, yeah.
Earth is the densest planet in the solar system.
Wait, really? The densest? I would have assumed Jupiter or Saturn. I mean, they're massive.
They are massive, but they're gas and ice giants.
They are.
Well, they're fluffy, relatively speaking.
Fluffy. I like that. A fluffy gas giant.
Exactly. Earth, on the other hand, is a compressed ball of iron, nickel, and rock. It is incredibly heavy for its size.
Yeah.
And that density, it tells us a lot about its violent origins. You don't get that dense without being forged in a serious, serious fire.
Which leads us to the origin story, the big splat, as some people call it. The research describes the formation of the moon not as, this romantic companion, but more like a crime scene.
It was a planetary fender bender, but on a scale that it defies human comprehension. The leading theory is that about 4.5 billion years ago, the early Earth, which was still basically a ball of molten rock, was slammed into by another protoplanet.
And this is the object they call Theia.
Yes. Named after the Greek Titan, who was the mother of the moon goddess. And you have to think of something roughly the size of Mars. It didn't just clip us. It was a cataclysmic off-center smash into the developing Earth.
So this wasn't an asteroid impact like the one that killed the dinosaurs. This was a planet-on-planet collision?
Correct. The energy release would have been, It would have liquefied the Earth's crust completely. It threw a massive, massive amount of debris into orbit. For a while, Earth probably had a ring system like Saturn, but made of molten rock and vapor.
And that debris, all that molten rock flying around us, eventually clumped together to make the moon.
Exactly. Gravity just did its work over, thousands, maybe millions of years. It started to coalesce. So when you look up at the moon at night, you are essentially looking at the scar tissue of that collision.
Wow.
It's made of a piece of the early Earth and a piece of Theia, all mixed together.
That creates such a real connection. It's not just a satellite. It's a part of us that got knocked off in this cosmic accident. But the scale difference is huge. The guide has this great visualization comparing the two.
It's striking when you see it laid out. Earth is 4 times larger than the moon by diameter, but surface area is where you really see it. The entire surface area of the moon is actually smaller than the continent of Asia.
That puts it in perspective. So if you could somehow unroll the moon like a carpet, it wouldn't even cover the largest continent on Earth. That's incredible.
It really is.
Now, earlier I mentioned that the days are getting longer. This connects back to the rotation in the moon, doesn't it?
It does, directly. It's a concept called tidal braking. The moon's gravity is incredibly powerful. It pulls on our oceans, creating the tides.
The high and low tides we see at the beach.
Exactly. But that friction, that massive sloshing of trillions of tons of water against the spinning Earth, it acts like a very, very slow brake pad. It's constantly creating a tiny bit of drag on the planet's rotation.
So the Earth is literally losing momentum.
It is. The rotation is slowing down. And as it slows, the moon is actually getting pushed into a slightly higher orbit. It's moving away from us by about 1.5 inches a year.
So do I need to adjust my watch? Is this something I should worry about?
Not unless you plan on living for another billion years. It's completely imperceptible to us day to day. But the math is solid. It shows that in about 1 billion years, a single day on Earth will be 27.5 hours long.
27.5 hours. Imagine what you could do with an extra 3.5 hours every single day.
Right.
You could finally finish that book you've been reading. Or let's be honest, probably just sleep more.
Well, the downside is you'd have to wait 1 billion years for it.
Yeah.
And the sun might be a bit hotter by then, which would be a problem. But it just goes to show that the planet's mechanics aren't fixed. They're evolving. The machine is running down in a sense.
Okay, so let's peel back the layers. If we could cut Earth open like a peach, what are we looking at? The research breaks it down into 3 main layers, but I feel like crust, mantle, core is a little simplistic.
It is, but it's the best way to visualize the huge temperature and pressure gradients. On the very outside, you have the crust. That's where we are right now. It's a thin, cool, brittle outer layer made of solid rocks and minerals.
Thin is relative, I guess, but compared to the rest of the planet, it's like the skin of an apple, right? It's incredibly fragile.
Extremely fragile. It's only, maybe 30 to 70 kilometers thick under the continents and even thinner under the oceans. And below that, you have the mantle. This is the thickest layer by far.
And this is hot rock.
Very hot rock. Now, a common misconception is that the mantle is just liquid lava sloshing around. It's not. It's solid rock, but it's under such immense pressure and heat that it can flow. The scientific term is plastic deformation.
So it flows, but over geological time.
Right. Think of it like warm, silly putty or asphalt on a really hot day. It moves, but only centimeters per year. And then right in the center, you have the engine room, the core.
And the core is split into 2 distinct parts.
Yes, and this is crucial. You have the inner core, which is a solid ball of almost pure iron and nickel. It is crushed solid by the weight of the entire planet bearing down on it. But surrounding that is the outer core, which is liquid metal.
And this liquid layer is absolutely critical for our survival.
It's the MVP of planetary habitability, no question. Because that liquid iron is constantly churning and swirling around, it creates a massive dynamo effect. It generates Earth's magnetic field.
That's the force field, the shield that protects us from solar radiation.
Without it, the solar wind, this constant stream of charged particles from the sun, would strip away our atmosphere and boil our oceans. Mars lost its magnetic field billions of years ago, and that's probably why it's a dead planet today. We literally owe our lives to that liquid metal sloshing around deep underground.
And the temperatures down there, I think this is where the user manual needs a big red warning label.
Oh yeah, the guide uses a great analogy. The core is as hot as the surface of the sun. We are talking roughly 6,000 degrees Celsius.
That is just wild. We were walking around on this cool, pleasant crust, maybe complaining that the air conditioning is broken, and a few thousand miles beneath our feet, It is the temperature of a star.
It explains everything. It explains why the planet is so restless. You have all that heat trapped inside from the planet's formation trying to escape.
Yeah.
Convection currents in the mantle carry that heat up, pushing and pulling on the brittle crust above.
Which brings us to section 2, the restless planet.
Tectonics.
The puzzle pieces.
Exactly. Because the crust is so brittle and the mantle beneath it is constantly moving, the crust is cracked. It's broken into these massive floating rafts called tectonic plates. You have the Pacific Plate, the huge Antarctic Plate, the Nazca Plate off South America, about a dozen major ones.
And they are essentially riding on that slow-moving conveyor belt of the mantle.
They are. And where they interact at their boundaries, that is where all the violence happens. That's where we get earthquakes, volcanoes, and mountain ranges.
This is where we get the Ring of Fire. It sounds like a Johnny Cash song, but in geological terms, it's a zone of absolute chaos.
It really is. It's a horseshoe shape, roughly 40,000 kilometers long, stretching all the way around the Pacific Ocean. It runs from New Zealand up through Indonesia, past Japan, across to Alaska, and all the way down the west coast of the Americas.
And the stats on it are just staggering. The data says that 90% of the world's earthquakes occur along this single belt.
90%. It's an incredible concentration of seismic energy.
And it's not just earthquakes.
No. Over 1,000 active volcanoes are located there as well. It's basically the seam of the planet where most of the pressure release valves are located.
Let's unpack how these plates interact, because the notes describe a few different ways they crash or slide past each other. It's not just a simple bumper car situation, is it?
No, it's more complex. It depends on the type of crust and the direction of movement. First, you have divergent boundaries. This is where plates are pulling apart.
Like the Mid-Atlantic Ridge.
Exactly like that.
Yeah.
As the plates pull apart, the pressure on the mantle below drops, magma melts, and it wells up to fill the gap, creating new oceanic crust. It's like a wound that's constantly healing itself with lava.
So that's the planet literally growing new skin.
Constantly. Then you have the opposite, convergent boundaries, where plates are colliding. But we'll get to that. The second type is a transform boundary. This is where two plates are just grinding past each other sideways.
No new crust, no crust being destroyed.
Right, they're just sliding. But the problem is, rock against rock isn't smooth. The friction is immense. They lock together. But the mantle underneath keeps pushing. So stress builds up for decades or centuries. Then snap.
And that's the earthquake.
That's the earthquake. The rock fractures. The plates might slip 10 or 20 feet in a matter of seconds. The San Andreas Fault in California is the most famous example of this.
And the third type, the convergent ones.
The third type is where things get really heavy, subduction zones. This is where one plate, usually a heavy, dense oceanic plate, crashes into a lighter continental plate and is forced to dive underneath it. It gets recycled back into the hot mantle.
And I assume that grinding action pushing a massive stone slab hundreds of miles into the earth is what triggers the really, really big quakes.
It is. The megathrust earthquakes, the biggest ones on record. And as that oceanic plate melts, it also creates the magma that feeds the volcanoes up above, like the ones in the Andes or the Cascades. This process also creates the deepest parts of the ocean, those deep ocean trenches, like the Mariana Trench.
So, measuring the power of these events, we use the Richter scale, which everyone has heard of, but the guide makes a really important point. It's logarithmic.
Yes, and this is key. A magnitude 5 isn't just one better or slightly stronger than a magnitude 4.
It's a whole different animal.
It's a completely different level of energy. Each whole number step up the scale represents a 10-fold increase in the measured amplitude of the seismic waves, and crucially, about 31 times more energy release. So magnitude 9 is not just a little stronger than an 8. It is vastly, catastrophically more powerful.
The guide gives a comparison here that it stopped me in my tracks. It says it would take 25,000 nuclear bombs to equal the energy released by a single magnitude 9.0 earthquake.
It just puts human power to shame, doesn't it?
Yeah.
The energy stored in these shifting plates is unfathomable. When the Earth decides to move, it moves with the force of thousands of our most destructive weapons, all released in a matter of seconds.
And sometimes that energy isn't just shaking the ground. It's molten rock punching its way through. Volcanoes.
Yes. And just for the sake of accuracy, we should probably distinguish between magma and lava. It's something people often use interchangeably.
Right.
Magma is the molten rock when it's still underground. It's pressurized and full of dissolved gases, like a shaken-up soda bottle. As soon as it breaks the surface and those gases can escape, we call it lava.
So the eruption is basically the planet popping the cork.
That's a great way to put it. And the volcano shape we all draw as kids, that classic cone.
Yeah.
That's just construction debris. Essentially, it's just layers and layers of cooled lava and ash building up over thousands of eruptions.
The source material takes us through a kind of greatest hits of volcanic eruptions, or maybe greatest catastrophes is a better term, because these events don't just happen in a vacuum, they change history.
They absolutely do. Take the Toba supervolcano eruption.
Yeah.
This happened about 74,000 years ago in what is now Indonesia. It wasn't just an explosion. It was a global climate-altering event. The guide says the ash and sulfur dioxide it threw into the atmosphere blocked out the sun for 6 years.
6 years without proper sunlight? That sounds like an extinction-level event.
It nearly was for us. Genetic studies suggest that human populations plummeted around that time. We were reduced to maybe just a few thousand individuals. We almost didn't make it. It caused a massive volcanic winter.
Then, in more recent history, you have Mount Tambora in 1815.
Another Indonesian giant. That's one that caused the famous year without a summer in 1816. The ash spread so far around the globe that it destroyed crops everywhere. It snowed in New England in June. There was widespread famine in Europe.
And wasn't that the summer Mary Shelley wrote Frankenstein? Because they were all stuck inside in Switzerland due to the terrible, gloomy weather.
Exactly. A geological event on the other side of the world led to the birth of the science fiction genre. Geological events shaped culture.
And we can't forget Krakatoa, 1883.
The loud one.
The really loud one.
Officially, the loudest sound in recorded history. It ruptured the eardrums of sailors 40 miles away. The atmospheric shockwave circled the globe multiple times. The eruption and the subsequent tsunami it generated destroyed nearly 70% of the island it sat on and killed tens of thousands of people.
And for those of us in North America, the reference point is usual Mount St. Helens.
May 1980. And that was unique because it was a lateral blast. An earthquake caused a massive landslide on the north face of the mountain, which basically uncorked the pressure on the side.
Not the top.
No, so it blew outwards.
Yeah.
The guide notes that the top 400 meters of the mountain were just gone.
Vaporized.
Blasted into a debris avalanche that traveled at hundreds of miles an hour, flattening forests for miles. But volcanoes aren't just history. They are active right now. We have giants living among us.
Like Mauna Loa in Hawaii.
The largest active volcano on Earth by volume. It doesn't look like a classic steep cone because the lava there is very runny. It has a low viscosity, so it flows for great distances. That creates these long, gentle slopes. It's called a shield volcano.
It's more wide than it is tall.
Exactly. And then you have Ojos del Salado in the Andes on the Chile-Argentina border.
That's the highest.
The highest active volcano in the world, sitting at almost 6,900 meters. And in Europe, you have Mount Etna in Sicily, which is almost constantly active. It acts as the kind of pressure valve for the Mediterranean. Its name actually comes from the Greek for I burn.
I burn, a very apt name.
Okay.
So that's the fire and the shaking. But let's look at what is left behind when things eventually cool down. Section 3 of our deep dive is all about the crust we actually walk on. The rocks, the gems, and the fossils.
Right. Geology 101. The guide breaks rocks down into 3 main types. You've got igneous, sedimentary, and metamorphic. And the key thing to remember here is that they're all made of the same stuff, just at different stages of a very, very long recycling process.
Let's run through them quickly. Igneous.
That's the start of the cycle. It's just cooled lava or magma. Obsidian is a great example that's mentioned in the text. It's volcanic glass. It cools so fast that crystals can't form, which gives it these incredibly sharp conchoidal fractures.
Sharp enough that it was used for arrowheads and even scalpels in ancient surgery.
Exactly. Then you have sedimentary rock. This is basically the recycling bin of the planet. Wind and rain erode the igneous rocks into sand, silt, and dust. It all settles in layers at the bottom of oceans or lakes. And over millions of years, the pressure from the layers above glues it all back together into new rock.
So sandstone, limestone.
Right. And this is where you find most fossils, because that gentle layering process can preserve the remains of plants and animals. And finally, you have metamorphic.
The shapeshifters.
The shapeshifters, yes. You take that sedimentary limestone, for example, bury it deep within the earth, subject it to intense heat and pressure for mountain building, but you don't melt it completely, and the chemistry and crystal structure actually change. It transforms into marble.
So it's a rock that's been cooked.
It's been cooked and squeezed into something new.
Now, scattered among all these rocks are the things we humans consider valuable, minerals and gems. The guide has a fun section on this.
It mentions diamonds, of course, which are just It's carbon, the same stuff as the lead in your pencil. But the atoms are forced into this incredibly rigid lattice structure by the immense pressure deep within the Earth. That's what makes them the hardest natural material known.
But it also highlights lapis lazuli, that deep, deep blue stone.
Yes. Historically, that was incredibly significant. The ancient Egyptians used to crush it up to make blue eyeshadow and pigment for paintings.
Yeah.
For a very long time, that brilliant ultramarine blue was more expensive than gold because lapis was the only source for it.
Wow. And then there's pyrite, fool's gold.
The great heartbreaker of the mineral world. I'm sure many listeners, myself included, have found a shiny rock as a kid and thought they were rich.
I definitely did. I had a whole collection of my gold.
It's a cruel trick because it has that glittering metallic luster, but the guide notes a telltale sign. That crystallizes in these perfect little cubes. Gold doesn't do that.
Yeah.
So if you see perfect shiny cubes, you can probably put away your retirement plans.
Good tip. But the coolest things found in rocks, for me anyway, have to be the fossils, the time capsules.
Oh, absolutely. The preservation itself is the miracle. The guide highlights amber, which is just fossilized tree resin. And yes, just like in Jurassic Park, insects and other small creatures can get trapped in it. The detail is stunning. The guide shows a photo of a dragonfly with its tissue-thin wing veins still perfectly visible millions of years later.
But let's talk about the weird stuff. The guide brought up a term I wasn't familiar with. Coprolite.
Fossilized poop. It sounds funny, and I guess it is, but it's scientific gold. It tells us exactly what prehistoric animals were eating. You can slice it open and find bone fragments or plant matter. It tells you if they were herbivores, carnivores, bone crushers.
It's a window into their diet. And the guide mentions the largest specimen ever found weighs 9 kilograms. That is a 20-pound piece of fossilized dung.
That represents a very large dinosaur having a very significant bathroom break.
Mm-hmm.
It really brings these creatures to life. They weren't just movie monsters. They were real animals that ate and digested and lived.
Speaking of bringing things back to life, we have to talk about the coelacanth.
The Lazarus fish. This is one of the great stories of modern biology. Scientists knew this fish from the fossil record. They had plenty of fossils. They thought it went extinct 60 million years ago, along with the dinosaurs. It was a done deal. It was a classic index fossil.
And then,
in 1938, a museum curator in South Africa gets a call from a local fisherman. Hey, I caught this really weird big blue fish with these strange lobe-like fins. She goes down to the docks, and there it is, a living fossil. A creature thought to be extinct for longer than humans have existed.
imagine the surprise. I mean, that's like finding a living T-Rex in your backyard.
It's the biological equivalent. And it just shows how much of the deep ocean is still completely unknown to us. We mapped the surface of the moon in detail before we ever mapped the bottom of our own oceans.
The source also gives us some specific dino details. It mentions the Stegosaurus and those famous bony plates.
Yes, those huge plates, some up to 60 centimeters high, running along its back. There's still a lot of debate about what they were for. Were they for defense, display to attract a mate, or were they like giant radiators to help regulate its body temperature?
And the pterodactylus.
A flying reptile. Not technically a dinosaur, but lived at the same time. The fossils are incredible because they show these tissue-thin wing membranes stretched over an elongated finger. They were masters of the air long before birds took over that niche.
Amazing. Now let's move from the rocks themselves to the landscapes they form. Section 4, Extreme Landscapes. The guide really challenges our basic definition of desert.
This is a common misconception that's worth clearing up.
Mm-hmm.
We hear desert, and we immediately think hot, camels and sand dunes. But the meteorological definition of a desert is purely about rainfall. It's about aridity. Any place that receives very little precipitation is a desert.
Which means
the largest desert on Earth is Antarctica.
the coldest place on Earth is the biggest desert.
Exactly. It's 14.2 million square kilometers of ice and snow, but it receives almost no precipitation. The air is simply too cold to hold moisture. It's a polar desert. So it's a desert made of frozen water.
That's a great paradox. And if Antarctica is the largest, what's the driest?
That title goes to the Atacama Desert in Chile. It's caught in a double rain shadow between the Andes Mountains and the coastal range. The guide notes that some weather stations in the Atacama haven't recorded a single drop of rain in over 400 years.
400 years? That's older than the United States as a country.
It's so dry, and the terrain is so harsh. It's got this reddish, oxidized soil, absolutely no vegetation in places, that NASA uses it to test its rovers and train astronauts for missions to Mars. It's the closest thing to an alien planet we have here on Earth.
But there are sandy deserts too, of course, and they have their own weird quirks. The guide mentions the singing sands in the Mojave.
Yes, in the Mojave Desert in the USA. It's a very strange acoustic phenomenon. When the wind blows, or when sand slides down the face of a dune, the friction between the very specific, uniform-sized grains of sand creates a vibration.
And it makes an actual sound.
It creates a low-frequency hum, or sometimes a high-pitched whistle. It literally sings. Early travelers used to think it was spirits or underground rivers. This is quite an eerie sound.
And then there is the empty quarter.
The Rub al Khali in the Arabian Peninsula. This is the largest contiguous sand sea in the world. It's an area of dunes larger than the entire country of France. Just endless, shifting dunes as far as the eye can see. It is one of the most inhospitable places on the user's manual map.
Let's pivot back to the poles for a moment. We touched on Antarctica being a desert, but the guide contrasts the Arctic and Antarctica in a way I found really helpful, because people do mix them up.
They do, and it's a crucial distinction. The Arctic, up north, is an ocean surrounded by land. The ice there is sea ice. It's floating on water. Antarctica, down south, is a continent. It's actual rock covered in a massive ice sheet that's up to 3 miles thick in places.
Land versus sea, and the wildlife is strictly segregated.
Strictly. You will never, ever see a polar bear and a penguin in the wild together, unless you are at a very confused zoo or looking at a very inaccurate Christmas card.
Right.
Polar bears are Arctic. They are the largest land carnivore, evolved to hunt seals on that floating sea ice. Penguins are almost exclusively Antarctic and in the southern hemisphere, like the emperor penguins mentioned in the guide. They huddle together for warmth through the brutal Antarctic winter. They evolved in the south where there were no land predators like bears to eat them.
What about humans?
The Arctic have a long history of human habitation. You have indigenous populations like the Inuit, who have lived there for thousands of years, developing these incredible technologies and cultures to survive the cold. Antarctica has no indigenous human population. It was never permanently settled. Today, it's just scientists and support staff.
And the structures those scientists build are fascinating. The guide shows the Halley-6 research station. It looks like something out of a sci-fi movie.
It's a piece of brilliant engineering. It's a British station, and it's built on these giant hydraulic ski feet.
Skis. The whole building is on skis.
The whole building, because the ice shelf it sits on is constantly flowing toward the ocean, and snow is always accumulating on top of it. If they built it on the ground, it would get buried and eventually crushed or fall into the sea. So with the skis, they can jack the whole thing up to stay above the snow, and if the ice gets too close to the edge, they can hook it up to bulldozers and just tow the entire base to a safer spot.
That is so cool. It's a mobile base. And then there's the Brazilian station, Comandante Ferraz.
Which looks more like a luxury hotel or a Bond villain's lair. It's all steel and glass, very sleek. It replaced an older station that burned down, so it's completely state-of-the-art.
Is there any plant life down there at all?
Very, very little. The guide identifies the Antarctic pearlwort as one of only 2 flowering plants on the entire continent. It's this tiny, tough little plant that forms these moss-like clusters in the slightly more sheltered parts of the Antarctic Peninsula. It's just clinging to life on the edge of the world.
Okay, let's move to greener pastures, literally. Section 5. Forests and mountains.
The lungs of the earth. Or maybe the air filters is a better analogy. The guide states we have about 40 million square kilometers of forest covering the planet. But, and this is a sobering stat, we are losing about 1 million square kilometers of that every single year.
That's a terrifying rate of depreciation on our planetary life support system. We really need to protect what we have, especially the giants. The guide mentions a tree named General Sherman.
The giant sequoia in California. It's the largest tree on Earth by volume. It's not the tallest or the widest, but it is the most massive living thing on the planet. It's estimated to be between 2,200 and 2,700 years old.
Let's put that in context for a minute. That tree was a seedling when the Roman Empire was just getting started. It was already a mature tree when Jesus was born.
Exactly. It has survived countless fires, droughts, and the rise and fall of civilizations. It's a living monument. And on the other end of the spectrum, from a single giant tree, you have a giant forest, the taiga.
The snow forest.
Right, it's this massive boreal forest that stretches in a ring around the top of the world, from Norway all the way across Siberia and into Canada and Alaska. It's full of hardy trees like pine, larch, and spruce, and it stores an absolutely immense amount of carbon in its soils and trees.
The guide also highlighted some weird forests, the Sundarbans.
That's the largest mangrove forest in the world, on the delta of the Ganges River in southern Asia. And what's unique about mangroves is that they live in this salty, waterlogged mud where there's no oxygen for the roots. So the roots have to grow up out of the mud, they're called nematophores, to get oxygen from the air. It looks like the whole forest is growing on a bed of spikes.
And what about the cricket forest in Poland?
Now that's a real mystery. It's a small grove of about 400 pine trees that all have this sharp 90-degree bend at the base of their trunks, and they all face north. Then they curve back up and grow straight.
Do we know why?
Nobody is 100% sure. It was planted around 1930. The leading theory is that human farmers intentionally manipulated the trees when they were saplings, maybe to create naturally curved timber for furniture or boat building. But then the project was abandoned during World War II, but nature just kept growing.
And Aokigahara in Japan.
The Sea of Trees. It grows on hardened lava from a past eruption of Mount Fuji. The ground is very uneven and rocky, and the trees are incredibly dense. It's famous for blocking out wind and sound. It's known for being unnaturally quiet inside.
From forests, let's go up to the mountains. The Earth's wrinkles.
Big wrinkles caused by those tectonic plates crashing into each other. You have the Andes, which is the longest mountain range in the world at 7,000 kilometers. It's the spine of South America.
And of course, the Himalayas, the abode of snow.
The highest range, containing 10 of the 14 highest peaks on Earth, including Mount Everest. But what I found really interesting in the notes was the age difference between these mountain ranges. The Himalayas are actually quite young, geologically speaking.
They're the rebellious teenagers of mountain ranges.
They are. They only started forming when the Indian subcontinent crashed into Asia about 50 million years ago. And they're still growing by millimeters per year as that collision continues.
Compare that to the Makanjo Mountains in South Africa.
The great elders of the planet. The guide says they are 3.6 billion years old. They're not tall and jagged anymore. They're worn down, green, and rolling. But they contain some of the oldest volcanic rocks on Earth. They've stood witness to almost the entire history of the planet, from the first single-celled life to us.
Now, if we want to go deeper than the mountains, we have to go underground, into the caves. Section 6, the hidden world.
This is the part of the user manual that deals with the interior plumbing of the planet. And the scale here is just as surprising as the mountains. You have Mammoth Cave in the USA, which is the longest known cave system in the world. Over 644 kilometers of interconnected tunnels have been mapped.
That's like a subway system for a major city, but carved by water and limestone over eons.
But for sheer size of a single chamber, it's Hang Son Doong in Vietnam. This place is unbelievable. It was only fully explored in the last decade or so.
How big is it?
The guide says the main passage is so wide and tall, you could comfortably fit a 40-story skyscraper inside it. You could fly a Boeing 747 through it without touching the walls.
A skyscraper. Underground.
It's so enormous that it has its own weather system. Clouds actually form inside the cave near the ceiling. It even has its own jungle growing inside where the roof is collapsed in a couple of spots, letting in sunlight.
And for sheer depth.
That would be Veryovkina Cave in the country of Georgia. It goes down 2,212 meters. That is over 2 kilometers straight down into the Earth's crust. Expeditions to the bottom take weeks. You have to set up camps underground.
The visuals in this section of the research are amazing too. The Cave of the Crystals in Mexico.
This place looks like Superman's Fortress of Solitude. It's a chamber filled with giant, translucent selenite crystals, some up to 15 meters tall and weighing tons.
But you wouldn't want to hang out there for a selfie?
Absolutely not. It's directly above a magma chamber. The temperature inside is nearly 60 degrees Celsius with 100% humidity. Without a special cooling suit, a human would die in a matter of minutes. It's one of the most beautiful and deadly places on Earth.
And Watomo in New Zealand.
The glowworm caves. The ceiling looks like a starry night sky, but it's actually millions of bioluminescent larvae, the larvae of a fungus gnat, hanging from the roof on sticky threads to catch prey.
Nature is just so weird, and sometimes people actually choose to live underground.
Coober Pedy in Australia. It's an opal mining town in the outback, and it gets so incredibly hot there, regularly over 40 degrees Celsius, that the residents realized it was easier to live in the ground than on it. They built their entire townhomes, churches, shops, even hotels underground in old opal mines called dugouts. It stays at constant, comfortable temperature year-round.
That's a perfect example of adapting to your environment. Now, we can't do a user's manual for Earth without talking about the fluid that makes it all work, water. Section 7, the blue planet.
Right, the water cycle is the global engine here. Evaporation, condensation, precipitation. It's a constant loop.
Yeah.
And the guide mentions a staggering number. The sun evaporates 1 trillion tons of water every single day.
1 trillion tons. That is a lot of weight being lifted up into the sky.
And it all comes back down eventually. It cleanses the air, it carves the landscape, and it fills the basins.
Yeah.
But the distribution is the real kicker. 97% of all the water on Earth is salty.
So we can't drink it.
Right. We can't use it for agriculture. Only 3% is fresh water. And of that 3%, most of it is locked up as ice in the poles and glaciers where it's deep underground.
Yeah.
So the liquid fresh water that's easily available for us in lakes and rivers is a tiny, tiny fraction of 1% of the total. We're living on the edge of scarcity.
Here's a fact from the notes that I really hadn't thought about before. The oceans weren't originally salty.
That's right. When the oceans first formed, about 3.8 billion years ago from water vapor condensing out of the atmosphere, and maybe some from comet impacts, they were fresh water.
So how did they get salty? Where did all that salt come from?
It came from the rocks. Over billions of years, slightly acidic rain falls on the land, and it dissolves minerals and salt out of the rocks. It all washes into the rivers. The rivers then carry those tiny amounts of salt to the ocean. The water in the ocean evaporates to become rain again, but the salt gets left behind.
It just concentrates over time.
Exactly. It's a 3.8 billion year accumulation of dissolved mountains.
That is fascinating. So the salt in the ocean is basically the ghost of ancient geography.
In a poetic sense, yes. That's a perfect way to put it.
Let's look at the specific oceans. The Pacific is the biggest and the deepest.
It's enormous. It covers more area than all the land masses on Earth combined, and it's home to the Mariana Trench, the deepest point on the planet.
But the Atlantic is saltier.
It is, slightly. And the reason is complex. But one of the leading theories involves the trade winds. They tend to pick up freshwater vapor from the surface of the Atlantic and carry it west across Central America, where it then falls as rain into the Pacific Basin. So there's a net transfer of fresh water out of the Atlantic, making what's left behind a little saltier.
And then there's the Sargasso Sea. I always thought this was just a myth or a region, but it's a physically distinct body of water.
It is. It's the only sea in the world with no land boundaries. It doesn't touch a coast. It's defined entirely by ocean currents, a huge swirling gyre that circle around it. It's just this patch of calm, warm, salty water that's distinct from the rest, floating in the middle of the North Atlantic. It's famous for the massive floating mats of sargassum seaweed that thrive there.
And of course, we have the rivers. The arteries of the continents, the Amazon, the Nile, the Mississippi.
The Mississippi flows through 10 U.S. states. It's a massive drainage system for the entire center of the continent. The Amazon, in terms of volume, is the undisputed king. It carries more water than the next 7 largest rivers combined. It pumps so much fresh water into the Atlantic that you can literally drink the ocean water miles from the coast.
Finally, let's talk about how we use this planet. Section 8, resources. How we power our civilization.
This is where the user manual aspect becomes really critical. We have renewable sources, wind, solar, hydro.
The guide notes that to power the entire Earth with solar panels, we would need to cover an area about the size of Spain.
Which sounds like a lot, but when you think about the total surface area of the planet, especially the deserts, it's achievable. It's an engineering and political challenge, not a physical impossibility.
But right now, we're still so heavily reliant on the non-renewables, the fossil fuels. Coal, oil, and gas. And there's a stat in here that really truly drives home what the term fossil fuel actually means. It stopped me cold.
This is the one that stuck with me too. It's easy to just, pump gas into our cars without thinking about it.
Yeah.
But the guide breaks down the biological cost. It says it takes roughly 28 tons of prehistoric plant and animal matter to make just 1 single liter of petrol.
Hey, let me unpack that. 28 tons. That's the weight of several elephants. That's a dump truck full of ancient biomass for 1 liter.
That's the incredible inefficiency of geological time. You have to think about it. For millions of years, plankton and algae die in the oceans. They sink to the bottom, they get buried. Most of it decomposes or scatters. You need massive, massive amounts of this raw biological matter, compressed and cooked under the right conditions for millions of years to get that concentrated energy density we find in oil.
So when I fill up my car's tank, say 50 liters, I am burning through, 1,400 tons of ancient life.
You are burning a literal mountain of biological history just to get to the grocery store.
That completely reframes the concept of consumption. We aren't just using a chemical, we are literally burning the Cretaceous period.
Exactly. And that's why the user manual has a huge warning label here. This isn't a battery that recharges on a human timescale. Once we burn that liter, Those 28 tons of ancient history are gone forever. The carbon is released, the energy is used, and that's it.
And we are digging this stuff up and other minerals at a frantic pace. The scale of our mining is literally visible from space.
The guide shows the Bingham Canyon mine in Utah. It's a copper mine. It's a hole nearly 1 kilometer deep and 4 kilometers wide. We are scratching the skin of the planet deeper and faster than any natural process, wind, rain, or erosion ever could.
And we've been doing it for a long, long time. The Ngwenya mine in Eswatini is 42,000 years old.
Humans have been scratching at the user interface of Earth for a long time, but it's only in the last 100 years or so that we've started to actually affect the operating system itself.
So what does this all mean? We've gone from the core all the way to the atmosphere. We've looked at the violently formed moon, the shifting plates, the singing sands, and the literal burning of ancient history.
I think the biggest takeaway for me is the interconnectivity. You can't separate the parts. The tectonic plates create the mountains catch the rain washes minerals from the rocks into the rivers carve canyons and fill the oceans and make them salty. The saltiness affects the ocean currents. The currents affect the global climate. The climate dictates where the deserts and the forests are.
It's one big, complex, interconnected machine.
It is. And as the user manual suggests, it's incredibly resilient. It has survived asteroid impacts, supervolcanoes, ice ages. The planet itself will survive this. But the specific conditions that allow us to live here, the thin, fragile Goldilocks zone, that is finite.
We are living on a crust that is constantly recycling itself, floating on a sea of fire.
Exactly. We are just passengers on a very, very active vehicle.
So here is a final thought for you to chew on, listener. We talked about how the Earth's rotation is slowing down. We talked about mountains growing by millimeters every year. We talked about continents drifting apart. If we can fast forward another 4.5 billion years, what does Earth even look like?
And maybe more immediately, given that 28 tons of ancient matter goes into every single liter of gas we burn, how much of the past are we willing to burn to fuel our present?
Heavy questions for a heavy planet. That's it for this deep dive into Earth, the user's manual. Thanks for listening.
Stay curious.